Okay, so last time we were talking about convolution. We're going to talk more about convolution today, talk quite a bit about it, and also talk about the larger picture of how we construct these convolutional neural networks. So just to review a little bit about the motivation for convolution, what we're trying to do. From one perspective, you could say perhaps we have a small pattern like this number 4 thing, and there's a larger image that contains a lot of stuff, but we're looking for the presence of things like this in the larger image. So maybe we would hope to find these different 4s. And so what we do is we take this little image, which we can call a template, and we slide that around this bigger image, and at different locations, what we do is we do a pointwise multiply between all the pixels in this little template and all the pixels underneath it in the image. We pointwise multiply them and we add them all together. And in some sense, that tells us whether there is something similar to this template at that location in the larger image. So we kind of do this. We move around at all the locations in the larger image, and we do this for every shift. And so we call the J1 and J2 are the indices of the top left corner of this template that we're moving around. And so what we do is we compute that output value for that J1, J2 pair. And we sort of assemble a new image that is indexed by these pixel indices J1 and J2, where that inner product between the template and the underlying image would be that pixel in this new image. Is that idea making clear kind of what convolution is doing? Okay, so that is described in this equation. And so here we see J1 and J2 are, they're the index here in the output image. They're also the top left corner of the location in the original image here, at which point we're doing the convolution, or let's say the inner product. And that inner product is done through this summation over indices K1 and K2. And then we have K1, K2 indexing over the locations in the template, as well as indexing the shifts relative to J1 and J2. Okay, so here's J1 and J2, and then J1 and J2, or J1 plus K1, and J2 plus K2 would be some pixel location inside the box. Okay, so this is super important to understand because we're gonna add to this. So, but understanding it is kind of a necessary step in going forward. So I just want to pause and make sure, are there any questions at all? What's happening in this equation? Is everybody understanding this? Okay, no questions? Okay. And then a little bit of terminology. So we saw that this operation, same one from the previous page, is called correlation in the signal processing literature. And it's related to something else called convolution. And the difference in correlation and convolution are these minus signs. These pluses get turned to minuses. And essentially that means it's like these would be the same operation if in the image X you flipped it both horizontally and vertically. If you flip if you flip the template horizontally and vertically, because then what happens is this K1 and K2, instead of indexing down and to the right, you would index up and to the left. So that's equivalent to flipping and reversing that template. So that's just sort of some terminology. What we're going to do in our neural networks is correlation, but for some reason, in the machine learning literature, they all call it convolution. So, but even though it's called convolution, it's really this operation here. And you have to be aware that if you go to like the signal processing toolbox in SciPy and you do correlate 2D, you're going to get this. But if you do convolve 2D, you're going to get this other operation with the flipped and reversed image. Okay. And another thing we talked about was there's different ways of handling what happens at the boundary. So it basically corresponds to how much you allow the template, which is this thing, to, how much you allow it to go outside of the original image. So what we call full mode convolution, you allow that template to go as far as possible outside the original image so that it's only touching the original image at 1 pixel. In valid mode, you do not let it go outside the original image at all. So it's constrained to only lie in the original image. In this case, there's only 4 possible shifts. There's that one, this one, this one, and this one. And so as a result, the output image only has 4 pixels. And then there's this same mode where, depending on the size of the kernel, you allow as much zero padding here so that the output image has exactly the same size as the input image. And this is probably the most common one, just because it makes it simple to keep track of the sizes as you go through the network. Okay. All right, and then these are just some examples with numbers. So any questions so far?
So is there any type in which padding is just done on left side or right side only?
No, I haven't seen that. I've just seen the padding be the same on both sides. Okay. All right, so let's talk a little bit about how we implement this in Python and see some examples. So for this, we need the SciPy signal package and the skimage package. The skimage package has this kind of famous image called Cameraman. People have used it for decades in the image processing literature. So we're going to load that image. And what's nice about Cameraman is it has some really nice sharp edges, and it has some vertical ones, it has horizontal ones, it has diagonal ones, and so that's kind of useful for some of the things we'll be looking at. So the first thing we're going to do is we're going to check out these different boundary effects. So we're going to come up with a kernel. This is how we build our kernel. This is just a 9x9 square rectangle where every value in that kernel or template has the amplitude 1/81 because there's 81 pixels total. So basically, if you sum up all the pixels in the template, they add up to 1. So you can think about it as doing an average. Wherever you move it, when you move, so that template's kind of boring. It doesn't look like this. It just has all equal pixels. When you move it somewhere and you do that inner product, you're just going to be averaging all the pixels in the image underneath it and reporting the average pixel over here. So that's what it's doing. As you shift it around, it just tells you the average of what's underneath it. Okay, so that's this. It's simple, but it does have an application. It could be used in denoising. So if this image had a lot of noise in it and you were looking for a simple way to average out that noise, if the noise is zero mean, what this filter will do is it will reduce the noise because you're just taking the average of the noise. And as you can see in these images, the problem with doing that is it makes the image kind of blurry because it just takes that average of 9 pixels, and as a result, it just makes it blurry. But that's sort of the trade-off you get for this very simple denoising method. I don't have noise here, but you would see that the noise is attenuated a lot at the expense of blurring. But what we're looking at here is just some of the other effects. So let's look at the boundary conditions. So we're going to do this convolution using the convolve2D, but we can tell it whether to do full, same, or valid mode. And so let's take a look at what happens at the edges of the image. So here we're zooming into the top left corner. We're showing the top left, I think it's 20 by 20 pixels here. And you can see in the original image, it's just gray all the way to the edge. Now, if I do full mode convolution, that means I'm adding a lot of zero padding. And when I zoom into the image here, you can see we get these weird artifacts in the image edge because like at this pixel over here, essentially my kernel has averaged all these zeros and 1 gray pixel. And the zeros are black, so this pixel is almost totally black. It's not totally black because it has this 1 gray pixel that was thrown into the average. And as I move in this way, it's like I'm moving my kernel in, and it's averaging less and less black pixels, more and more gray, and so it just gradually gets more gray. Okay, and the size of this image is reported here. Okay, the original image was 512 by 512. The size of this is 520 by 520. So you can see it got bigger because of the zero padding. Okay, any questions on this? Is it making sense? Okay, and then if we look at the valid mode is giving a smaller image than the original one. It's 504 by 504. But just like the original, it doesn't have any of these edge artifacts. And then the same image is kind of in between. So the size of the input and output are the same. You do have some zero padding effects, but they're not as bad as in this case. And these images are all the same except for what happens around the edges. Okay, any questions? Okay, so another thing we can play with is the size of the kernel. So we could try a 9 by 9 kernel like the previous page, or we could try 15 by 15. And as you can see, what happens is everything gets more blurry with the larger kernel because essentially we're averaging a larger width. We're averaging, 225 pixels versus 81, and that just makes everything more blurry in the output. If we had noise, you would see that there would be less noise here than here because it's going to do a better job of averaging out that noise. Okay, and we can also look at a kernel that's a little bit less boring. So instead of making a kernel that's just uniform amplitude at all the pixels, we could make what's called a Gaussian blur kernel, which if you took like a slice across this dimension, you would see there's sort of a Gaussian shape here, or if you took a slice across this dimension, there'd be a bell curve shape here, or altogether this is like a two-dimensional Gaussian kernel, and it has a strongest pixel in the middle, weakest pixels on the edges. You have to specify the standard deviation, which will specify the width of the effective kernel. And if you really do want to see the tails here, got to make sure that the size is larger than, let's say, 2 times the standard deviation plus 1. Otherwise, it will just clip things out, and if you clip enough, it will just look almost uniform. So if we look at the pictures here, this is the uniform kernel that's 9 by 9. This is the Gaussian one that's 9 by 9. This is less blurry than this because the effective kernel width here is really something like this compared to the 9 by 9, which would be effectively a wider kernel. So even though they have the same absolute width, this one is effectively like a smaller kernel because of all the black pixels around the edges. Same thing with 15 by 15 uniform and Gaussian. Okay. And another thing we can do with these, it's a little bit more interesting, is edge detection. And in particular, we can detect horizontal edges or vertical edges pretty easily by making our kernels look like this. So here we have a kernel with positive numbers on the left, negative numbers on the right, and zeros in the middle. And so imagine that this is sitting on top of an image where you have a vertical edge. Maybe you have dark here and light here. And you can see what's going to happen is the dark pixels, those are small values. The small values will be multiplying positives. The large values, light, will be multiplying negatives. And so overall, that will give you a strong negative response, at least if you're doing correlation. If you're doing convolution, then you have to remember to flip and reverse this guy. So actually, it ends up being the opposite. So since we're focusing on convolution in this slide rather than correlation, if we have a horizontal change going from dark to light, as I just described, dark to light, then that would be for a vertical edge, and you would notice that the output of the filter should be positive. On the other hand, if you have a horizontal change going from light to dark, the output should be negative. What happens if you have a change vertically? Let's say this is dark to light. What kind of an output would you get in that case? 0, right? Because you'll see everything cancels. So this filter detects detects vertical edges, and then this one, which is transposed, this one is what you could use to detect horizontal edges. Okay, these are called Sobel filters. And you might ask, like, why are these not all just 2, 2, 2, minus 2, minus 2, minus 2? Yes, that would work fine as well. This is done to make this a little bit smooth, smooth in the vertical direction. And if you had 2s there, it would just be a little bit less smooth, and so it could cause some ringing artifacts and other visually unpleasant things. So let's try this out. So we're going to do, again, convolve 2D. We'll do valid mode for now, and this is how we can make those kernels. Those are we just manually specify those 3x3 arrays in NumPy. And what you can see is when we do this GX, that was the kernel that detected vertical edges. You can see here it's, this, okay, where should we look? Let's look at this, because this is totally vertical. When we look at that guy, you can see going from dark to light, there's that little white line. That would be positive. On the other hand, going from light to dark, you'd see there's a black line on that side, negative. Okay, and notice that this is the filter to detect horizontal changes, and you can see it does not respond at all to the vertical edges of the building. On the other hand, we have some horizontal edges, like here, that are invisible to this filter, but are clearly present in that filter's output. And then we have diagonal ones, which you can see in both filters. Okay, so it's a simple edge detector. Any questions so far? Okay. Oh yeah, and then so this is convolution. And so with correlation, remember that means we're flipping the kernel. So for these kernels, if I flip this horizontally and vertically, so flipping it vertically does nothing because it's symmetric vertically, but flipping it horizontally just changes the sign. So that will change the polarity of the output. And so what you see is when we go from convolution to correlation, these black edges turn to white edges, and vice versa. Or white here turns to black there, just as expected. Right. So, okay, so that's just sort of like a little background on convolution. Now let's zoom out to talk about bigger things. How are we going to use these, and what else are we going to do in a typical convolutional neural network? So let's take the bird's eye view for now. So this is AlexNet, which we'll be studying quite a bit. So this is, remember that was the first network that 2012 that, beat all the other non-network approaches in that competition. So, and remember that these blue things, those are not system blocks, those are like signal blocks. They show essentially the shape of the signal at every layer in the network. So this is the input signal, which are images of 224 by 224 pixels. They're color, so they have 3 channels, red, green, blue. The first layer is going to do, you could say it has 3 sublayers. It has a 2D convolution with a bunch of kernels. We'll talk more about that in a moment. But I think you understand basically how 2D convolution works now. Then, like we saw in the last unit, it goes through an activation, some nonlinearity like a ReLU. And the other thing that happens in these convolutional neural networks is subsampling or pooling, which is something that's used to reduce the number of pixels as you go through the network. So you start with these 224 by 224 images, but after the first layer, notice that they have shrunk to 55 by 55. So basically, each of these 2 dimensions, you took essentially like 1 out of every 4 samples to go from here to here. So you threw out 3/4 in each dimension, or 1 out of 16 pixels, really. So you lost a lot in terms of the pixel resolution, but you went from 3 colors to, you could say, 96 colors. These are not colors that we humans can interpret, but the neural network can understand them. And there are various animals out there that can see with many more than 3 colors. So it happens in biology too, but we don't call these colors, we call them channels. So you would say that the input has 3 channels and that the features in the first layer have 96 channels. And these are design things. Probably the creators of this tried different numbers of channels versus the layers, and they settled on these. But overall, what you tend to see in these networks is you start, so the number of channels in your input, of course, is not up to you. If you're dealing with color images, it has to be 3. But as you go through the network, you generally use more and more channels and fewer pixels. So eventually, by the time they got there, they had 13 by 13 in the pixel domain, but 256 channels. And these are all convolutional layers with things like activation, and the subsampling is responsible for the change in the number of pixels. Okay. Then, at this point, they essentially, what we call flattened or unraveled this. We call these tensors. I'll talk about it more in a second. But you can think of this as it's like a 3D structure of values, and if you just kind of unravel that into a single vector, it's going to have 13 times 13 times 256 entries, and those features now go into this MLP. So this is just exactly what we saw in the last unit. So this is going to be, you're going to have a matrix multiply followed by another ReLU, another matrix multiply followed by a ReLU, and so on. So this is exactly what we saw in the last unit. Non-convolutional, we call these dense layers, and then these are the convolutional processing here. The reason for the name dense is that when you look at the matrices that are here, if you just looked at them, you'd notice that there's essentially non-zero values everywhere. When you look at a convolutional layer, you can write convolution as a matrix multiplication, and when you do that, you'll notice that would be for a 1D convolution. You'd notice that it essentially has a banded structure we call a Toeplitz matrix, and so all these would be zeros out here. So this is not a dense matrix because it has tons of zeros in it. But these would be dense matrices because they don't. So that's where this name comes from. Yeah.
So if I'm thinking this correctly, like going from the first layer, we basically have like 96 separate kernels that are each kind of like, they're going to be trained eventually, right?
Great question. So we're going there soon. But to answer your question, it will actually have 3 times 96 different kernels. But we'll talk about that in a moment.
Okay.
You have a separate kernel for every one of these and one of these.
So you don't just have a 2-dimensional kernel, like a 3-dimensional kernel for that?
You could think of it that way. There's different ways to think about it, but yeah, we'll talk about that in just a moment. Okay, so basically, let's just talk about tensors. This is really just some notation. A tensor is nothing more than a multi-dimensional array, and you've already been working with these. So for example, a matrix is just a 2-dimensional array of numbers. That's an example of a tensor. A color image, where you have the height, you have a certain number of pixels corresponding to the number of pixels in the height of the image, the width, and the channel, where maybe the channel is red, green, blue. That's an example of a tensor. That would be a degree 3 tensor. This is a degree 2 tensor. Or we've also been talking about these. What if you have a batch of images? So each one of the images has a certain height, a certain width, certain numbers of channels, but then there's a whole batch of them. So there's another index over the batch. So that would be a four-way tensor. That's what we're actually dealing with when we train things. Okay, so, and then just some terminology. So the number of dimensions, like this would be 4, that's called the degree, or sometimes the order, or sometimes the rank. And by the way, when you talk about the rank of a tensor, like a generic tensor like this, it has nothing to do with the rank of matrices. Unfortunately, they use the same term, but they're unrelated. In fact, even talking about something like the linear algebra rank of a tensor is really difficult once you go beyond 2 dimensions. There's different ways to define it, but it's much more complicated. The shape of the tensor essentially tells you, it's the list of numbers that tell you the sizes of all those. So for example, if I have a 10 by 20 by 4 structure, then you would say its shape is 1024, and you'd say because there's 3 things, you'd say its degree is 3. And I think you've already seen this with NumPy, because in NumPy, if you do like something dot shape, it just basically lists this, reports that. So you've already seen these ND arrays in NumPy, these are just tensors, and in PyTorch, they're called dot tensor. Okay, so now we're going to talk a little bit more about exactly what happens in the convolutional layer. So the first thing is the weights of the tensor, which basically all the kernels together. You can think about it as a 4-degree tensor, degree 4 tensor. So the way that we organize them in PyTorch, and they have to be organized exactly this way, otherwise PyTorch misinterprets what you want to do. These 4 dimensions, or at least the shape, would be the number of output channels for that layer, the number of input channels, and then the size of the kernel. So that would be the weights. Those are the things, the parameters you're learning. You also have a bias for that layer, and the bias, all it does is it adds a single number to all the pixels for each of the output channels. So, so the bias vector is just a one-dimensional vector with Cout elements, just one number for every output channel. Okay. So that is basically what the weights are, the trainable weights. And the inputs are going to have, they have to be configured this way. So the first element, or the first dimension is basically the batch dimension. So if you have a single image, not like a whole batch of training images, the dimension here would be 1. Then you have the number of input channels. This is the input tensor, so this is the number of channels in the input. And then these are just the number of vertical and horizontal pixels coming in. And then the output tensor is going to be organized in a similar way. You're going to have, this is the output tensor. I is going to index into the batch. M is going to index into the number of output. That's the output channel index. And then these are the spatial indices, same as at the input. Okay, so here's what's actually happening. The way I like to think about it is, let's imagine we freeze a particular output channel and a particular input channel. So at that point, M and N are frozen. You can just sort of forget about them for a moment. All that's left is convolution. You can see what remains here is just convolution the way we saw it before. So when we think about every particular input channel, output channel pair, there's just a standard convolution happening there. Then, for a given output channel, you sum the results of the convolution over all the input channels. So let's come back to this picture over here. So as we said, one way to think about it now is there's 3 times 96 different 2-dimensional kernels. And if I want to ask, like, the very first kernel, what is it doing? It's the kernel that is essentially between the first channel here and the first channel here. There's also another kernel that's taking us from the second channel here to the first channel here, and a third one that's taking us from the third channel here to the first channel here. I might have said that wrong. So you have 1 to 1, 2 to 1, and 3 to 1. So all those 3 kernels are going to affect what's happening in the first of these 96 channels. And essentially what we're going to do is we're going to take, the red, convolve it with that kernel, add it to the green, convolve it with its kernel, and add that to the blue, convolve it with its kernel, which will give us what's in that very first channel. So does that make sense? Okay. Now, if you want to think about those three scalar kernels that are all contributing to this guy, you can think of them as a color one if you want, because you could just say, well, those are the three colors of that kernel, and then we can plot them, and I'll show you plots of what they look like. You can do that in the first, but you can't do that over here because we can't visualize 96 colors. But yeah, but you can kind of get an appreciation for how many kernels there are, right? So like to take us from here to here, we have 96 times 256 different kernels that we're training. Yeah, so this is, so that's basically the equation that we have for convolutional layers. So this is a super important equation. We really want to be able to understand this. And the way that I understand it, again, is for the moment, at first I just say, let's fix M and N. Then when you look at what else is there, that's just a standard two-dimensional convolution, which I think we can understand. And now, if I fix M and consider there's C in different convolution results, all I'm going to do is just add them all together to find what's in the mth output channel. And I do that, for every of my C output channels. This whole operation happens identically for every batch index I. So the batch index is not very important. It appears here in the outputs, here in the inputs. The kernels themselves are not dependent on the batch, right? They're the same kernel is applied to every batch element. And then here, this is just that bias term, which is just a different scalar applied to all the pixels, but it's a different one for every output channel. Okay, so that's essentially what convolutional layers do. There's a nice visualization of what's happening. Former student sent me this link. It's pretty cool. I'm not going to spend time on it here in the lecture, but if you want to click on this, it gives sort of a different way of understanding this that might be useful to you. Okay, any questions on what's happening here in convolutional layers? Yeah.
So we're basically trying to make the network learn the kernel.
The network learns all the kernels. It's doing this, it has some overall task. It could be classification. And the kernels, of the first layer are affecting the features of that first layer, and those features are going through the kernels of the second layer, and finally they're all affecting the output, and they all have an effect on the output. And we're trying to train them all together jointly, all to be a good classifier.
Yeah, but it's like when you explain the examples, like the Sobel filters or something.
Yeah.
Yeah. There we knew what we wanted to do.
Yes.
And now we don't, so we train the network.
Exactly, yes. In those examples, we were told what the kernels are. Now we're trying to learn the kernels. Okay, so again, I would like to talk a little bit about the PyTorch ordering conventions. So PyTorch very specifically wants the weight tensor to be organized this way: number of output channels, number of input channels, and then vertical, horizontal. And it wants the input tensor to be organized this way: batch index, channel index, vertical, horizontal. And the output tensor is organized the same way, except instead of number of input channels, you have number of output channels. Now, when you look at what's happening in skimage, it wants a different ordering convention. So first of all, it doesn't work with batch elements. It's not trying to train anything, so it's not working with batches. So when you have a color image, its framework or its format is height, width, channel. Okay, so when you, and maybe this is how you start. Maybe you load in your data in skimage, and later you want to apply it in PyTorch. You have to do some juggling to get the formats, to work with each other. So you're going to have to take what's in this location and you're going to have to move this to the front so that you can do that in NumPy with the transpose command. And then you're also going to have to add this index. So even if you have just a single batch element, a batch size of 1, because we're going to do a simple experiment, you can't give PyTorch a 3-way tensor because it's going to be like, I don't know what you're talking about. I only know about 4-way tensors. And so what you'll have to do is you'll just have to reshape that 3-way thing as a 4-way thing, and it will append an extra dimension to the front that will have size 1. So now it knows that this is a 4-way tensor, not a 3-way tensor. And now it knows how to deal with it. So we'll see that in the examples, but I just want to kind of emphasize that you have to, for these different toolboxes, you have to speak their languages. Otherwise, of course, you get completely the wrong results. Okay. All right. So any questions? Any more questions on convolutional layers? Okay. So let's move on to the next idea. So we said that 2D convolution is one thing that happens. Activation, we talked about activation. We'll talk about it a little bit more, but not right now. But we talked about like the ReLU activation, which looks like this. This is really good for deep networks because it avoids the vanishing gradient problem that you would get with a sigmoid or tanh network. Let's talk about subsampling and pooling, which are the ways that we reduce size. Here we went from 224 by 224 to 55 by 55. Later we'll reduce size by another half, again by another half, and so on. So there's basically 3 popular ways to do that. In all cases, you're pruning the number of pixels. You're just trying to shrink the size of the image in the spatial domain. And so the simplest one is known as subsampling. So it's like this. You have an image. I'll draw just a very small 4x4 image. And what you say is that in each one of these regions, so this will be a 2x2 region, you just say, I'm going to keep the top left pixel, and I'm going to throw the others away. So I'm going to, by doing this, I'm going to shrink from something that had 16 pixels to have something that has 4. Okay, so that's subsampling. And this size 2x2, here they call that the stride. But the stride actually has a slightly different meaning, which it's the right way to think about stride is by how far you shift this to the right or down. So here the stride is 2 because this little 2x2 window, you're shifting it to the right by 2, then you're shifting it down by 2, and so on. So that's what the stride is how much you shift it. So this particular operation, subsampling, because you know what you will keep and you know what you will throw away, it doesn't make sense computationally to compute these convolutional outputs, because remember this is happening after your convolutional layer. It doesn't make sense to compute those outputs if you know you're going to throw them away. So this is implemented together with convolution in a smart way so that when you do the convolution, it just simply only computes those outputs and it never computes the other ones. That way you're not wasting any multiplies. Okay, so it's implemented as part of convolution. It's not like a separate thing, a separate little block that you would load from your PyTorch library. It's actually something you specify when you specify your convolutional layer. Okay, so any questions on the subsampling idea? So it's just a crude way of subsampling your image, making it, a lot smaller. And in signal processing, like if you took 5200, maybe 3050, I don't know, this is called downsampling.
Is there a relationship between like the kernel, how much it's shifting, or what its size is relative to the...
There is for these pooling, which I'll talk about in a moment. But for this, there's not. They're fixed. So if you have, if I had like a 3x3, then I would shift it over and that would be 3 by 3. So it's just like, you can't independently specify the size of this and the shift.
So the subsampling is taken then from the kernel, like the dimensions of the kernel?
Oh, the kernel size is totally separate.
Oh, okay, it is separate.
The kernel size can be as big or small as you want. So this is just saying like which of the pixels coming out of the convolution will you keep and which will you throw away. Yeah, kernel size can be anything. Okay, so now, but maybe you'll see what I was trying to say with max pooling. Rather than just keeping, let's say, the top left pixel of every region, you keep the largest value no matter where it is. So you would perhaps look over this square and you'd look at the 4 values, and whichever is largest, that's the one you keep. And then you look over this square, and whichever is largest of those 4, that's the one you keep, and so on. That's called max pooling. And there's also average pooling, which is just to say you just take the average of all those pixels, you report the average, you take the average of these, and so on. Now, with both max and average pooling, you actually can decouple how much you shift, which is the stride, from the size of the region that you do the max or the averaging over. So I'll show you an example here. So on the top, this would be when you have k equals 2. K is the size of the window. Here k equals 3. And the shift, or the stride, is 2 in both cases. Okay, so what we're going to do here is, this is my little 2 by 2 region, k by k, or 2 by 2 region. I'm going to look for the maximum pixel here, which is obviously 5, report that. Then I shift over, so my stride is 2, so I move this to the right by 2. I look at the maximum there, which is 4, I report that. And then I also go down by 2 because my stride, S is 2. I report 4, and so on. Now, I could have had a 3 by 3 window. And in this case, when I look over the max here, it's still 5. But I could have a stride that's only 2, which means I shift this down only by 2. See, here I can have a stride that's different from the window size. Here, too, I shift to the right by 2, not 3. So I can have these values can be different. Okay, so we have a k by k region and a stride of S. And this last one is called, in signal processing, it's called decimation. If you've taken 500, maybe 3050 talks about it too, for sure. 500 talks about that. Okay. Yeah, and when you do this on every channel, on every batch item. It just, and independently on every channel, meaning that, if in one channel this was the largest element, then in the next channel, maybe a different one is the largest element. So it's, it just depends on the values in each channel. Okay, so that's subsampling. Any questions on that? Okay. Okay, so let's come back to our picture here. So part of the reason we're doing this subsampling is that just sort of intuitively, we start out with this big image, but at the very end, we don't have images at all. We have classes, like these are the 1,000 classes in ImageNet, right? So we somehow have to go from the world of images, to the world of no images and classes. And so what we're doing here is we're just gradually making the image size smaller and smaller until at some point what's over here you don't even think about them as images anymore because there's no more horizontal and vertical pixels. Just lists of numbers. And the numbers somehow have meaning when you think about classes. So gradually you go from here to here by reducing the size of the number of pixels, reducing spatially. But if that's all you did, you would not have enough information. Here you just need to collect a lot of different features. So to combat the loss of spatial size, you increase the channel size. So it's like you're trading off from a lot of pixels, few channels, to less and less pixels, more and more channels. Okay, so that's why we're doing this. Anyway, last thing to talk about are the dense layers. essentially these are exactly what we have seen in the previous unit. So the last convolutional layer will report a tensor of this shape. So batch elements, number of output channels, pixels by pixels. And then what we're going to do is we're just going to flatten this into, we're going to flatten this stuff into a vector. We're going to do this separately for every batch element. So we're going to now get, you could say, a matrix where we have elements in a batch and just a certain number of new elements where the number of elements in this vector is just this three-way tensor, flattened. So C out times N1 times N2. Okay, and then the dense layers or the linear layers, they look exactly like what we saw in the last unit. So here's our matrix W, and this is our activation. It has two indices because there's a batch index, and then there's the index across the different hidden nodes. So these are like the input nodes, these are the output nodes. So, so basically as you're going through your network, actually this tensor changes from a degree 4 tensor to a degree 2 tensor at the stage where your network transitions from convolutional layers to dense layers. Okay. So it's just exactly like we saw in the last unit. Flattening is that reshaping operation.
So how do we decide number of convolutional layers?
That's a great question. So we'll talk about the history. At the beginning, they wanted to make it deeper, and they faced problems, and this was kind of as deep as they could go, but it was very deep at the time relative to what came before. And then we'll see that using various tricks and things, they were able to make them more deep because that they found that was working better. But we'll go through all the tricks. We'll go year by year and see the advances they made and exactly how things progressed. Yeah. Eventually, nowadays, you can do this with thousands of layers if you want. Depth. It's possible. Okay. All right. Any other questions? Okay. All right, so let's talk about why are we doing convolution? Why not just do dense layers everywhere? And a lot of it has to do with they're much more efficient. If you count the number of parameters or count the number of multiplies you have to do, they're orders of magnitude more efficient. So let's look at just an example. Let's look at the second layer of AlexNet. So not the very first one, but the second one. So in the second one, we're going from something that has 96 channels and a 55 by 55 spatial, pixels to something that has 256 channels and 55 by 55. We will eventually do pooling to shrink this dimension, like max pooling. But for now, we're just focusing on the convolutional part, which doesn't actually, we're doing same mode convolution, so we're having the same image size, but we're growing the number of channels. And here I have stars for the batch. It doesn't really, what we're talking about on this page, it holds for any batch size, so it's not important. Okay, so let's think about a convolutional layer. How many weights and how many biases do we need? So remember that in a convolutional layer, you can say that there's a single kernel for each one of these 96 channels and each one of these 256. There's a single kernel, and that kernel is going to be a k by k. Right? So the total number of parameters would be 96 times 256 times k1 times k2. Right? So this is the total number of parameters that we have to learn in this convolutional layer. Is that making sense? Where we got that number? Right? So it's every kernel has k1 times k2. They're usually square, but in general they could be rectangular. So k1 times k2, and then C out times Cn, because that's the number of kernels we have to design. The number of biases is not a big deal. It's C out, which is 256. Okay, so in AlexNet, in the second layer, they use 5 by 5 kernels. And so if you plug in 96 times 256 times 5 times 5, you get 600,000 different weights and 256 different bias coefficients. Okay, sounds like a lot, but let's look at what happens if instead of a convolutional layer, we would have used a fully connected layer, a dense layer. So now, the way to think about that is you have to flatten everything. So essentially, this is like a matrix multiply. So the size, the number of coefficients at the input is going to be this, right? For every, let's say for every batch element, I'm going to have Cn times N1 times N2 different elements that I need to put through my dense layer. Is that making sense? Okay. And then, oops, I meant to erase. Okay. And then how many output elements? How many here? It's actually not square, it's tall. So that is going to be this. C out times N1, oops, times N1 times N2. Okay. So how many coefficients are now in the matrix? How many coefficients are in there?
N1 and 2, C and N1.
Exactly. It's this number times this number. And so that is this number, C out times Cn times N1 squared times N2 squared. And if you multiply those things together, you get 200 billion weights compared to 600,000. 600,000 is doable. 200 billion in that one layer is not doable. Okay, way too many. Even the number of biases is kind of crazy. So this is why, in some sense, you could say you're forced to use convolutional layers rather than fully connected layers. They're just so much more efficient, not only in terms of the number of weights, but if you also think about the number of multiplies, because to compute, let's say, the first element in that output vector, you have to do all of those weights times all of these. That's just a lot of multiplies. So from the perspective of memory and parameters, which has an effect on overfitting and all that stuff, as well as computation, convolutional layers are just way, way more efficient. They're also they have this translational invariance idea, which is the whole pattern matching idea. This little pattern that we're searching for could be anywhere in the image. So it makes sense to have a small kernel that I can move around everywhere. Convolution just makes sense as something that we might want to do with like visual processing. And we said it's actually what happens in our brains too. So biologically, we've evolved to use the same tricks. Okay. All right, so any questions on this page, convolution? Okay. All right, so let's talk about, just quickly about implementing some of this stuff in Python. So this is the code to do the edge detection stuff. So let's see. So this is how we would do it in PyTorch. We already saw how to do it in SciPy Signal. Okay, so we have to set things up for the right sizes in PyTorch. So let's establish how many images we're working with. Basically, like how many images are in our batch? Just one, just this guy. How many input channels? Grayscale, so it's 1. So the batch shape is going to be like this: number of images, comma number of channels, comma number of rows, number of columns. And number of rows and number of columns we can get from im.shape. And that's 512 by 512. And so now what we're going to do is we're going to take this im, this is our image, we're going to reshape it according to this 4-way tensor size. And so originally the image was just a 512 by 512 matrix. Once you reshape it, it's this 4-way tensor that has shape 1, 1, 512 by 512, right? So it takes the same amount of memory to store it. It's just like now PyTorch knows that this is a 4-way tensor, whereas if you just gave it something that's 512 by 512, it would not be able to know what to do with it. It'd be like, well, you only told me 2 of the 4 dimensions. What are the rest? Okay, so creating convolutional layers. Okay, we know how to create them in NumPy. So then the way that we work with PyTorch is we could start by building a 2D convolution. So this is the neural network library in PyTorch. When we create this, instantiate this, we have to tell it how many input channels, how many output channels, and what's the kernel size. So we're going to do both of these simultaneously in one layer. So number of input channels, since it's a grayscale image, will be 1, but we're going to have 2 output channels because we're going to get the 2 different gradient operators. The kernel size is just going to be 3 by 3. We can do that by gx.shape. Okay, so now we have this thing that's instantiated in PyTorch, and when you do this in PyTorch, it just randomly initializes all the weights and the bias. So what we're going to do next is we're going to extract them from the model using this state dictionary thing, model.stateDictionary. Then we unpack them from the state dictionary. The weight, we'll call it W, the bias, we'll call it B. And then we're going to replace the values in W and B with these GXs. But of course, we have to convert GX from NumPy to a torch tensor. And then we're going to stick this into, these are our 2 different output channels, and they both have the same, there's only 1 input channel. And we're going to replace all the other elements with that 3 by 3 matrix. And we do that for these 2 different output channels. We're going to use bias of 0. We don't want to shift the image at all. So now we have things set up in W and B. Now we got to put them back into our state dictionary, and we got to load the state dictionary back into the model. And now the model's set up. Now we're ready to process the data. Because the data is the right size and it's a torch tensor, our model will know what to do with it. It's as simple as this, and then what comes out is going to be a tensor that has 2 different images, and one of them will be the vertical edges, one is the horizontal edges. In order to plot it, we have to bring things back to NumPy with this detach. But finally, when we're back in NumPy, then we need to convert from these 4-way tensors back to 2-way matrices that we can plot, and we get these images just like we would expect. And these are exactly the same ones we got from Correlate 2D, not from Convolve 2D, right? Because we're actually doing correlation, not convolution. Even though PyTorch calls it convolution, it's really correlation. Okay, so then I'll save this for next time. We can do a more sophisticated example where we have a color image. We want to have 4 different output channels. In each one, we essentially want to convolve this with a red kernel, with a green kernel, with a blue, with a pink one. And we'll see how we can do that in PyTorch. Out of time for today, so see you guys on Wednesday.